I want to show identically that the curl of E for any charge distribution vanishes. So let's begin with Coulomb's law, which tells us how to compute the electric field for any charge distribution. So E of R can be written as 1 over 4 pi epsilon naught times the integral of rho of R prime, which describes the charge distribution, times the vector R over the magnitude of R cubed, and that's integrated over d tau prime. The variable script R is just the difference between the point that I want the electric field at minus the point that we're looking at the charge distribution at. So script R is just R minus R prime. The integral is over R prime. The curl that we're taking above is going to be with respect to the unprimed variable R. So that means that we can write the curl of E of R is equal to the curl of the constant times the integral rho R prime R cubed d tau prime. Now since the curl is with respect to the unprimed variables, I can bring it inside the integral and have it only operate on the variables R. So that looks like this. Notice that it doesn't depend on R prime, so I bring it through. It's only going to operate on my script R over R cubed and not on d tau prime. So I need to compute that curl. I'm going to use an identity, so let me write down the identity I'm going to use. It's the curl of F times A, so that is a scalar function times a vector, is equal to the scalar function times the curl of A minus the cross product of A with the gradient of the scalar function. So when applying the identity, I'm going to use F as 1 over R cubed and A as the vector R. So let's first compute the curl of R. That's going to be equal to the curl of R minus R prime, or the curl of R, since the derivatives don't operate on R prime. R prime is just a constant with respect to those derivatives. This can be shown to be identically equal to 0. I'll leave it to you. The curl of the position vector is identically 0. Now let me compute the gradient of 1 over R cubed. It's going to equal x hat times the x derivative of 1 over R cubed plus y hat times the y derivative of 1 over R cubed plus z hat times the z derivative of 1 over R cubed. So these are all very similar, so let me just take the x derivative. So that's going to be the x derivative of 1. Let me write out what R is, or the script R is. R cubed. And that's just equal to d, the derivative with respect to x, times 1 over x minus x prime squared plus y minus y prime squared plus z minus z prime squared. That's all to the 3/2. That's going to equal, taking the derivatives, minus 3/2 times 2x minus x prime, all times the whole thing above, to the 5/2, which is going to be 1 r to the 5th. So collecting it all together, I get that d by dx of 1 over r minus r prime cubed is just equal to minus 3x minus x prime all over r to the 5th. Now, the same thing can be done for x, for the y and the z. I won't repeat it here, but they're very similar. 1 over r minus r prime cubed. That's just going to be minus 3y minus y prime over script r to the 5th. And then d by dz is just going to be minus 3 z minus z prime all over script r to the 5th. So pulling all this together, I get that the gradient of 1 over script r cubed is just minus 3 r over r to the 5th. So if you go back, you can look at putting the derivative, the unit vectors back in with my derivatives, and you'll see that you just get the script vector r on top again. Now I return to the identity I started with, where I identified f and a as 1 over the magnitude of script r cubed and the vector r respectively. And that identity can be written as 1 over the vector r divided by its magnitude cubed is the curl of r times 1 over r cubed minus the vector r, script r, crossed into the gradient, which is minus 3 r over r cubed. So we showed that the curl of the vector script r is 0, but also the vector r, script r crossed with itself, has got to be 0. So therefore both terms are 0. Collecting everything, we see therefore that since both terms in the integral that I was doing vanish, the curl of E must vanish identically.